After a star explodes, you'd expect nothing to be left, just emptiness. But there's something still there, something the size of a city that weighs more than the sun, something so dense that if you scooped up a spoonful, it would weigh as much as a mountain. Tonight we're going there. I wonder where you are right now. Late at night with the lights off, early morning half awake. If this quiet wonder pulls you in, stay a little longer, maybe leave a like, drop a comment, or simply listen. Now, settle in, breathe slowly, and let's begin. Long before the collapse, before the cataclysm, before the crushing density, there is a cloud, a quiet, sprawling nursery made not of brick or stone, but of gas dust and the leftovers of other long-dead stars. These are stellar nurseries, and if you zoom out far enough, they look like delicate wisps floating in the darkness, painted across the void in shades of red and blue and violet. Beautiful, yes, but inside they're anything but still. Gravity is busy, very, very busy. A star begins not with a bang, but with a sag. Over time, sometimes millions of years, particles in a molecular cloud begin to gather, drawn to each other by gravity's invisible pull. Imagine grains of sand rolling together, slowly on a trampoline, each one tugging at the others, warping the fabric beneath them. More mass means more gravity, which means more attraction, which means even more mass. It's a feedback loop, gentle at first, then faster, then inevitable, and it ends with something glowing. At the heart of the collapsing cloud, pressure builds, temperature rises. Atoms that were once drifting lazily through space are now packed tightly together, jostling, colliding, heating up. And then at a certain point, when the core is dense enough and hot enough, something magical happens. Hydrogen atoms begin to smash together, not gently, not politely. They collide with such force that they fuse, combining to form helium and releasing energy in the process. This is nuclear fusion. This is the magic that turns a clump of dust into a baby star. That energy pushes outward, fighting against gravity's inward pull. The result is a delicate balance, a kind of cosmic standoff. The star is suspended between collapse and explosion, glowing gently in the vastness of space, held together by forces that are locked in an endless tug of war. And just like that, a star is born. But not all stars are created equal. Some are small and quiet, red dwarfs that simmer for trillions of years, without much fuss, burning their fuel so slowly that they'll outlive galaxies. Others, like our sun, live moderate lives, about 10 billion years of stable warmth and light, neither too hot nor too cold, neither too fast nor too slow, steady, reliable, comfortable. And then there are the giants. These massive stars, the future parents of neutron stars, live fast, burn hot, and die young. They're dramatic, overachieving, and quite frankly exhausting. To qualify for neutron star parenthood, a star needs to start off with at least 8 times the mass of our sun. Some of them are dozens of times more massive, and they go through their fuel like there's a cosmic deadline. They fuse hydrogen into helium, then helium into carbon, then carbon into oxygen, and on, creating heavier and heavier elements in their cores. Each stage burns faster than the last, like a candle flame being fed pure oxygen. The star doesn't slow down, it accelerates. Silicon fuses into iron in a matter of days. Days. After millions of years of patient burning, the final act happens in less than a week. And here's where it gets interesting. Eventually, the fusion chain reaches iron, and this is where everything changes. You see, iron is special. Unlike lighter elements, you can't extract energy by fusing iron atoms together. It just doesn't work. In fact, trying to fuse iron costs energy. It's like trying to power a light bulb by stuffing it with used batteries. Nothing happens, and everything just gets hotter and more unstable. So when a star builds up a core of iron, it's like reaching the end of a highway with no exits. The engine stalls, fusion stops, and with no outward pressure to counterbalance gravity, the star begins to fall inward on itself. But we'll get to that in another moment. Let's linger just a bit longer on the life of a massive star, because honestly, it deserves some appreciation. These stars are cosmic forges. Almost everything you're made of was born inside a star like this. The carbon in your DNA, the calcium in your bones, the oxygen you're breathing right now. It was all forged in the heart of a massive star billions of years ago, in temperatures and pressures we can barely imagine. Stars don't just light up the universe, they build it. Atom by atom, element by element, they take the simplest ingredients, hydrogen and helium, and turn them into the stuff of planets, oceans, flowers, and people. You're not just in the universe, you are the universe, quite literally made from it. And massive stars do this with flair. They spend their lives sculpting the space around them, forming beautiful bubbles of hot gas, carving out cavities in the interstellar medium, and sometimes pairing up with equally dramatic partners in binary systems. They spin rapidly, throw off enormous stellar winds, and pulse in brightness as their internal dynamics shift and evolve. They're brilliant, unpredictable, and destined to change. They're not so different from teenagers, really. Bright, full of energy, burning through resources, faster than anyone thinks is reasonable. A little chaotic, a little unstable, living their best lives while they can, because they know on some cosmic level that it won't last forever. And just like teenagers, massive stars are in their prime. The most beautiful, the most intense, the most alive they'll ever be. But it's a short-lived glory, because what makes one of these massive stars destined to become a neutron star instead of, say, a black hole? The answer lies in the delicate balance between mass and resistance. If the collapsing core is not quite massive enough to become a black hole, but too massive to remain a white dwarf, it finds a strange middle ground. The pressure from all those neutrons packed together halts the collapse, at least temporarily, and what's left is a neutron star, a remnant about the size of a city, yet more massive than our sun. But that moment of choice, that fork in the road between neutron star and black hole, depends on how much mass the core has when the end finally comes. If it's between about 1.4 and 2.3 times the mass of our sun, it becomes a neutron star. Any heavier, and gravity wins completely. The core collapses past the point of no return, and a black hole is born. It's a narrow window, a fragile boundary. The difference between becoming the densest object we can still observe and vanishing beyond the event horizon is just a matter of a few solar masses. And yet in that narrow window, neutron stars exist. They are the survivors, the in-betweeners, the remnants that held on. Stars are the great recyclers of the universe. They take simple ingredients, hydrogen, helium, and turn them into the building blocks of everything we know. They spend their lives quietly resisting gravity, only to be undone by it in the end. And in their final moments, they light up the universe with a brilliance that echoes across space and time. It's peaceful in a way, poetic. A star collapses and something new is born. Not quite alive, not quite dead, just different, quiet, dense, mysterious. So, the next time you look up at the night sky, remember that some of those twinkling points are the calm survivors of ancient chaos. They've seen their suns die, their cores implode, and now they spin in silence, holding secrets heavier than anything on Earth. All of that from a simple cloud of dust. But nothing lasts forever, not even in space. Eventually, for the universe's most massive stars, that delicate harmony unravels in a matter of seconds. And when it does, something truly spectacular happens. The star explodes. For billions of years, a massive star burns, like a furnace converting lighter elements into heavier ones, in a process known as nuclear fusion. It starts with hydrogen, the simplest and most abundant element in the universe. The star fuses hydrogen atoms into helium-releasing energy in the process. This energy pushes outward, keeping the star puffed up like a balloon against the relentless inward pull of gravity. But hydrogen doesn't last forever. When it runs low in the core, the star begins to fuse helium into carbon into oxygen, then oxygen into neon, into magnesium, into silicon, and finally, silicon into iron. Each step up the periodic table happens faster and faster. In the star's final days, these fusion processes might only last a few years, months, or even just days. And then it hits the iron wall. Iron is special in a frustrating kind of way. Unlike the lighter elements, you can't extract energy by fusing iron atoms together. Instead of releasing energy, fusing iron consumes it. It's like trying to power a light bulb by stuffing it with used batteries. Nothing happens and everything just gets hotter and more unstable. Once the core of the star fills with iron, the fusion engine effectively shuts down. Gravity, which has been held in check for millions of years, suddenly has nothing to push back against. The balance breaks, and when that happens, the star begins to fall in on itself. Now this is where things speed up dramatically. In less than a second, the core begins to collapse. Temperatures soar to over 100 billion degrees. The pressure becomes so intense that electrons are forced into protons, creating neutrons and neutrinos. This process is called electron capture. It turns the core into a soup of densely packed neutrons, while a flood of neutrinos, nearly massless ghostly particles, escape in all directions. Imagine a bowling ball collapsing into a marble in the blink of an eye. That's the kind of scale we're talking about here. The core, once thousands of kilometers across, compresses into a dense sphere only about 20 kilometers wide. And in that same instant, the outer layers of the star, no longer supported by fusion, crash inward at a significant fraction of the speed of light. But this inward collapse doesn't go on forever. When the falling material hits the incompressible core of neutrons, it rebounds. It's like trying to crush a diamond with a pillow. The outer layers slam into an unyielding wall. This rebound, combined with the outward rush of neutrinos, creates a shock wave, and that shock wave punches through the collapsing star, blasting the outer layers into space in a cosmic detonation known as a supernova. Now let's pause for a moment and talk about those neutrinos. Because they're extraordinary, during the core collapse, trillions upon trillions of neutrinos are born. They stream outward at nearly the speed of light, passing effortlessly through the rest of the star, through the explosion, and keep going through planets, moons, people. Because neutrinos rarely interact with anything at all. They're ghosts, nearly massless, nearly invisible, nearly undetectable, and yet trillions of them pass through your body every second. That's not an exaggeration. It's a gentle, invisible truth of everyday life. Right now, as you're listening to this, neutrinos from the sun, from distant supernovae, from the Big Bang itself, are streaming through you. You don't feel them. You never will. But they're their silent witnesses to the violent births and deaths of stars. A supernova is frankly absurd. For a brief period, sometimes just a few seconds, a single exploding star can outshine an entire galaxy made up of hundreds of billions of stars. The energy released in those few seconds is more than our sun will emit in its entire lifetime. If that sounds excessive, well, stars do love a grand exit. To an outside observer, this explosion looks like a sudden brightening in the sky, followed by a slow fade over weeks or months. But inside the star, it's chaos. Shock waves rip through the outer layers. The star's material is torn apart, scattered across light years. Elements forged in the star's core, carbon, oxygen, calcium, even iron are flung into the cosmos. These elements will go on to form new stars, planets, and maybe even life. In fact, every atom of iron in your blood came from a supernova. Every bit of calcium in your teeth, every speck of oxygen in your lungs. That's the poetic part of stellar death. It's also cosmic recycling. The end of one star becomes the beginning of countless other things. The explosion also sends ripples through space-time itself. These are gravitational waves, subtle distortions in the fabric of the universe, radiating out from the dying star. We've only just begun to detect them in recent years, but they tell us stories that light alone cannot. Supernovae are rare in our galaxy, perhaps only one every 100 years, but their light can be seen across vast distances. Some of the most famous historical records of guest stars in the night sky were actually supernovae. Ancient astronomers from China, Japan, and the Middle East recorded bright new stars appearing for days or weeks before fading away. In one case, a supernova observed in the year 1054 left behind the Crab Nebula, still visible today through a telescope, and at its center, a pulsar, a spinning neutron star, left behind by the explosion. From the calm to the catastrophic, the life of a massive star is a slow burn, followed by an astonishing finale. For millions of years, it held itself together, fusing elements and glowing steadily. And then, in its final moments, it collapses, explodes, and scatters its essence across the universe. It's strange, really, that such violence can lead to such beauty, that something so devastating can be the source of new beginnings. But the universe is full of these contradictions, explosions that create, deaths that give life, stillness born from fury, and at the center of it all, a small, dense remnant, quiet now, but full of secrets. But not all of the star is destroyed. At the heart of the explosion, something remains. Let's talk about what survives. At the heart of the explosion, something remains. If the original star was massive enough, at least 8 times the mass of our sun, the collapsed core will survive the blast, and depending on its exact mass, it will either become a neutron star or, if even more massive, collapse further into a black hole. But we'll save that darker path for another day. Today, we're staying with the neutron star. Right after the supernova, this newborn neutron star is incredibly hot, over 100 billion degrees. But it cools quickly, radiating away energy through neutrinos and light. It spins rapidly, often several times per second, and its magnetic field intensifies to unimaginable levels. In just a moment, the gentle fusion-powered glow of a living star is replaced with a dense, spinning magnetic corpse, packed tighter than anything else in the universe short of a black hole. From the outside, it's hard to grasp just how violent this process is. But if you were a neutrino, born in the heart of that collapsing core, you'd be ejected at nearly the speed of light. You'd pass effortlessly through the rest of the star, through the explosion, and keep going through planets' moons. People, because neutrinos rarely interact with anything at all. So, what exactly is this thing that's left behind? A neutron star packs more than the mass of the Sun into a sphere only about 20 kilometers wide. That's roughly the size of a small city. You could walk across it in a few hours if you could avoid being crushed, vaporized, or turned into subatomic mist. To put it another way, imagine taking a jumbo jet and compressing it down to the size of a sugar cube. That's the kind of density we're talking about. 1 cubic centimeter, about the size of a dice, would weigh as much as Mount Everest. And yet this whole thing is sitting quietly in space, spinning, cooling, and occasionally flashing its magnetic beams, like a celestial lighthouse. It's a paradox, really. Something so small, yet so massive. Something that should collapse further, yet doesn't. Something that was once a star burning brightly, now silent and dark, yet still powerful, beyond imagination. So, why doesn't it collapse further? What stops it from becoming a black hole? The answer is a strange kind of pressure. Not the kind you feel when you've got a deadline coming up. No, this is quantum pressure. More specifically, neutron degeneracy pressure. It's a consequence of the Pauli exclusion principle, a rule from quantum mechanics that says no two identical particles can occupy the same quantum state. In other words, neutrons don't like to be crowded. They push back, and that push is enough to stop gravity unless there's too much mass, in which case, hello black hole. But if the mass is just right, somewhere between about 1.4 and 2.3 times the mass of our Sun, this neutron degeneracy pressure is enough to hold up the star's weight. And so, the collapse halts, the core stabilizes, the explosion continues outward, but at the center, something new has formed, a neutron star. Not quite alive, not quite dead, just different. It no longer burns hydrogen. It no longer shines with the warm glow of fusion, but it exists. It spins, it cools, it endures. Quiet now, but full of secrets. A small, dense remnant of something that was once a giant, now compressed into a sphere you could drive across in less time than it takes to watch a movie. From the calm to the catastrophic, from fusion to compression, from light to darkness, this is what remains. This is the heart that survives. It's strange, really, that such violence can lead to such beauty, that something so devastating can be the source of new beginnings. But the universe is full of these contradictions, explosions that create, deaths that give life, stillness born from fury, and at the center of it, all this tiny, impossibly dense object, a neutron star, spinning in the dark, holding on to secrets we're only beginning to understand. But what makes a neutron star so strange? What's actually inside it? It's strange, really, that such violence can lead to such beauty, that something so devastating, the collapse of a star, the explosion that tears it apart, the scattering of its atoms across light years, can be the source of new beginnings. But the universe is full of these contradictions, explosions that create, deaths that give life, stillness born from fury, and at the center of it all, a small, dense remnant, quiet now but full of secrets. Think about it for a moment. A supernova is one of the most violent events the universe can produce. Temperatures soar into the billions. Shock waves rip through layers of matter. Elements are forged and flung into space. And yet, from that chaos, something stable emerges. Something that will endure for billions of years, spinning quietly in the dark long after the flash of the explosion has faded. It's a paradox. Violence creates beauty. Destruction gives birth. The end becomes the beginning. Neutron stars remind us that the universe doesn't follow our neat categories of life and death. A star doesn't simply die and disappear. It transforms. It becomes something else, something stranger, something that holds within it the memory of everything it once was, compressed into a space so small you could fit it inside a city. And in that transformation, there's a kind of poetry. Because these stars, these massive, brilliant giants, they started life as nothing more than clouds of gas, just hydrogen and helium drifting through space, barely held together by their own gravity. And over millions of years, they gathered, compressed, ignited. They burned steadily, fusing hydrogen in their cores, glowing softly, drifting along with their galactic neighbors. They were ordinary in their own way, just another point of light among billions. But then they changed. They grew. They burned through their fuel faster and faster, building heavier elements, glowing brighter, hotter, more intense. And at the end, they didn't simply fade away. They exploded. They scattered their essence across the cosmos. And they left behind something extraordinary, a neutron star. Now they sit as relics, as monuments, testaments to the violence and wonder of stellar death. They are the survivors, the remnants, the quiet witnesses to processes so extreme that even our best physics struggles to describe them. Neutron stars are strange, but they are also beautiful. They are the middle children of stellar evolution, not quite stars, not quite black holes, but with their own fascinating personality. Their compact records of physics, at the edge, full of secrets we're only beginning to understand. They don't burn like stars. They don't consume like black holes. They simply exist, spinning, cooling, waiting. And yet, despite their strangeness, despite how alien they seem, neutron stars are not distant from us. Not really. Because the iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was forged in the fiery deaths that give birth to neutron stars. We are in a very real way made from the same stardust. The atoms in your body were once inside a star. They were created in fusion reactions deep within a stellar core. And when that star died, when it exploded in a supernova, those atoms were scattered into space. They drifted through the galaxy, for millions of years, eventually finding their way into a new cloud of gas and dust. That cloud collapsed, forming a new star. That star had planets. One of those planets was Earth. And billions of years later, here you are, made of stardust, made of supernova remnants, made of the same material that forms neutron stars. That's the connection. That's why we find them so mesmerizing. Not just because they're extreme or strange or powerful, but because they're part of our story. They are distant, yes. They are aliens, yes. But they are also family, cosmic cousins forged in the same fires, shaped by the same forces. When you look up at the night sky, some of those twinkling points might be neutron stars. You can't see them. With the naked eye, they're too small, too dim, too far away. But they're there, spinning silently in the dark, holding secrets heavier than anything on Earth. And every time you take a breath, every time your heart beats, you're carrying a piece of them with you. The iron that helps carry oxygen through your blood was made in a supernova. The calcium that keeps your bones strong was forged in a dying star. The carbon that forms the backbone of every molecule in your body was created in stellar fusion. You are not separate from the universe. You are part of it. You are it. And maybe that's why we find neutron stars so compelling. Because when we study them, when we try to understand them, we're also studying ourselves. We're learning about our origins, our history, the long, slow process that turned simple hydrogen into stars, into planets, into life, into consciousness. Neutron stars are strange, yes, but they're also a reminder that even in collapse, even in death, the universe creates something remarkable, something small, something dense, something that spins quietly in the dark, asking questions through its very existence. They challenge us. They remind us that the universe is still full of mysteries, that there are places where our understanding breaks down, where the rules we thought we knew no longer apply, where matter behaves in ways we can barely imagine, and where the fabric of space-time itself is stretched to its limits. Neutron stars are the legacy of stellar evolution, the final gift of a star that lived fast and burned bright. They are proof that transformation, not death, is the true nature of the cosmos, that endings are always beginnings in disguise, that nothing is ever truly lost, only changed. And as we stand here on this small planet, orbiting an ordinary star, we can look out into the darkness and know that we are connected to it all, to the stars that died billions of years ago, to the neutron stars spinning in the void, to the atoms that make up our bodies, and the light that reaches our eyes. We are stardust contemplating stars, and in that contemplation, there is wonder, there is beauty, there is a kind of peace that comes from understanding even just a little how all of this fits together, how the universe recycles itself, how death feeds life, how violence gives birth to stillness, how something as simple as a cloud of gas can become a star, and a star can become us. Neutron stars are not just objects to study. They are not just data points on a graph or signals in a telescope. They are part of the story, our story, the story of how the universe makes itself over and over again in an endless cycle of creation and transformation, from the calm to the catastrophic, from light to darkness, from fusion to compression, from life to death to life again. That's the lesson of the neutron star. That's the message written in its incredible density, its impossible spin, its quiet endurance. Nothing ends. Everything transforms. A neutron star is small, just about 20 kilometers across. That's roughly the length of a leisurely morning drive through the countryside. But what it lacks in size, it more than makes up for in density. This is not just a heavy object. This is the heavyweight champion of the universe, short of black holes. It's a place where matter has been crushed so tightly that atoms no longer resemble anything we've ever seen on Earth. If the laws of physics had a basement neutron, stars would live in it. So, what's actually inside one of these things? What happens to matter when it's compressed to such an extreme degree? What does the interior of a neutron star look like? Let's peel back the layers and see what's inside. Because if you think what we've covered so far is strange, just wait. Inside the neutron star, where matter reaches its limits, let's start with the basics. Imagine scooping up a teaspoon of neutron star matter. Not a big ladle, just a gentle, dainty teaspoon. That single spoonful would weigh about 6 billion tons. That's roughly the mass of Mount Everest crammed into something small enough to stir your tea with. Only, of course, you couldn't stir this matter. You couldn't even get close to it. It would drop straight through the planet, slicing clean through the mantle core, and whatever else got in its way before exiting out the other side. Then it would probably continue falling through space, radiating menace and gravity in equal measure. Think about that for a moment. A teaspoon, 6 billion tons. Mount Everest in your hand, if your hand could somehow survive, which it absolutely could not. This isn't just dense. This is density taken to its logical extreme and then pushed several steps further. This is matter stripped of everything we recognize as normal and compressed into a state that shouldn't exist but does. This is what happens when gravity decides it's done being polite. To put it another way, imagine taking a jumbo jet, engines, wings, seats, passengers and all, and compressing it down to the size of a sugar cube. That's the kind of density we're talking about. 1 cubic centimeter, about the size of a dice, would weigh as much as Mount Everest. Roll that dice across a table, and the table wouldn't just break, it would vaporize. The floor beneath it would collapse. The planet beneath that would crack. And if somehow the dice kept its form and kept falling, it would tunnel through the Earth like it was made of tissue paper. Now scale that up. A neutron star is roughly 20 kilometers across. That's about the size of a city Manhattan maybe, or central London. And yet packed into that space is more mass than our entire sun. The sun, which is so large that over 1 million Earths could fit inside it, is now compressed into something you could drive across in 20 minutes. It's absurd, truly absurd. And yet neutron stars exist. Thousands of them scattered throughout our galaxy, spinning quietly in the dark. Let's talk about what that density actually means for anything or anyone unlucky enough to get close. The gravity on the surface of a neutron star is, to put it mildly, intense. If you were somehow able to survive long enough to stand on it, which for the record you would not, you would weigh more than 200 billion times what you do on Earth. That's a 2 followed by 11 zeros. If you weigh 70 kilograms here on Earth, you would weigh about 14 quadrillion kilograms on a neutron star. That's not a typo. 14 quadrillion. Your bones would be crushed instantly. Your organs would liquefy. Every atom in your body would be compressed beyond recognition before you could even think about saying, ouch. But let's say, just for fun, that you dropped something less fragile. A marble, perhaps. You hold it at waist height and let it go. On Earth, it would take about half a second to hit the ground, and it would land with a gentle clink. On a neutron star, that marble would hit the surface at several thousand kilometers per second. That's fast enough to vaporize the marble on impact, and quite possibly your waist too. The energy released would be equivalent to a small explosion, all from dropping a marble less than a meter. This is not a place where the usual rules apply. This is a place where gravity has gone completely overboard. And if you somehow wanted to leave, if you somehow survived long enough to realize what a terrible idea visiting a neutron star was, you'd face another problem: the escape velocity. On Earth, if you want to break free of the planet's gravity, you need to reach about 11 kilometers per second. That's why rockets are so large and require so much fuel. They're fighting gravity every inch of the way up. On a neutron star, the escape velocity is around 150,000 kilometers per second. That's more than half the speed of light. Think about that. More than half the speed of light just to leave the surface. If you wanted to launch a rocket from a neutron star, you'd need fuel tanks the size of planets. And even then, the rocket would probably melt from the sheer friction of trying to accelerate that fast. The energy requirements are so extreme that it borders on the impossible. This is what makes neutron stars so extraordinary. They take the concept of heavy and redefine it entirely. They take the rules we thought we understood about matter and gravity and space-time, and they push them so far that we're forced to invent entirely new physics just to describe what's happening. A neutron star is small, just 20 kilometers across, but what it lacks in size, it more than makes up for in presence, in weight, in the sheer crushing force of its existence. It's the heavyweight champion of the universe short of black holes. And even black holes can't claim to be this dense, while still being something we can observe, study, and at least in theory, touch. Not that you'd want to, but this raises an obvious question. If neutron stars are this dense, this heavy, this gravitationally intense, what are they actually made of? What is neutron star matter? Because it's not just compressed atoms. It's not just tightly packed elements. It's something stranger. Something that exists at the very edge of what matter can be, before it stops being matter altogether. So let's peel back the layers and see what's inside. Because if you think what we've covered so far is strange, just wait. But what is neutron star matter exactly? What happens to ordinary stuff when gravity goes completely overboard? Let's peel back the layers. Let's peel back the layers. Starting at the surface, we find something that barely qualifies as a surface at all. The outermost layer of a neutron star is called the atmosphere, though it's nothing like the air we breathe. It's only a few centimeters thick. A few centimeters. That's about the width of your hand. And yet, within that impossibly thin layer, conditions are so extreme that our everyday understanding of physics starts to break down. The atmosphere is made of plasma, a mix of electrons and atomic nuclei whipped into a frenzy by incredible gravity and magnetic fields. This isn't air. This isn't even hot air. This is matter in a state of barely controlled chaos. Hot, dense crackling with radiation. If you could somehow put your hand into it, your hand would cease to exist in less time than it takes light to cross a room. Light behaves oddly here. Because the gravitational field is so intense, photons trying to escape the star are redshifted, stretched into longer wavelengths before they finally break free. Even color takes a beating in this environment. A photon that started out blue might escape as red, or infrared, or something even less energetic. The star isn't changing color. Space-time is. This air isn't the kind you'd want to breathe. Not that you'd get the chance. Beneath the atmosphere is the outer crust. Now, crust might sound comforting, perhaps even edible, but this is no golden pastry. This is no gentle outer shell. The outer crust of a neutron star is a layer of ultra-dense crystalline nuclei packed together like sardines in a sardine can. Only the can has been stomped on by an entire planet. These nuclei are surrounded by a sea of free electrons. The gravity is so strong here that if you dropped a marble from waist height, it would hit the surface at several thousand kilometers per second. We've already covered that disaster. But what's remarkable is that even at these densities, even under this crushing pressure, the outer crust is still technically solid. It's a crystal, a lattice, an ordered structure, not unlike the atomic arrangements you'd find in a diamond or a piece of metal. Except here, the lattice is made of iron nuclei, nickel nuclei, and other heavy elements, all locked into place by the sheer weight pressing down on them. And yet, despite being solid, it's also incredibly brittle. The stress on this crust is immense. It's constantly being squeezed, warped, and twisted by the neutron star's rotation, its magnetic field, and the tidal forces from any nearby companions. Every so often, the stress becomes too much. The crust cracks. When that happens, we call it a starquake. The neutron star equivalent of an earthquake, only far more violent. These starquakes can release more energy in a fraction of a second than the sun emits in a year. They cause the star to glitch, to suddenly speed up or slow down. We'll come back to that later. For now, just know that even the crust of a neutron star is not a stable, peaceful place. Deeper still is the inner crust, and here things start to get truly strange. The pressure here is so great that electrons start merging with protons inside the nuclei, turning them into neutrons. These neutrons begin to drip out of the nuclei, forming a sort of neutron-rich soup that coexist with nuclear clusters. It's a strange halfway place, part solid, part liquid, part question mark. Scientists call this the neutron drip region, and it's exactly as surreal as it sounds. The nuclei are still there, but they're leaking neutrons, like a sieve leaks water. These free neutrons move around, flowing between the solid nuclear clusters, creating a hybrid state of matter that doesn't exist anywhere else in the universe. And then we come to one of the weirdest parts of the neutron star, the pasta layer. No, this isn't a joke. Physicists, after working with brutally complex nuclear models for years, finally said, "Fine, it looks like spaghetti. Let's just call it that." Oh, and so they did. In this region, between the crust and the core, atomic nuclei arrange themselves into long rods, flat sheets, and blobs. Depending on the shape, they've been nicknamed spaghetti, lasagna, gnocchi, and even Swiss cheese. This isn't culinary whimsy. These structures emerge from the fierce competition between the strong, nuclear force and gravity. The nuclear force wants to hold protons and neutrons together in tight clusters. Gravity wants to crush everything into a uniform blob. The result is nuclear matter that's denser than anything on Earth and organized into some of the strangest shapes in the universe. Spaghetti, long, thin rods of nuclear matter aligned like fibers in a muscle. Lasagna, flat sheets of nuclei stacked like pages in a book. Gnocchi, rounded blobs clustered together like bubbles in foam. And Swiss cheese, a lattice of voids with nuclei forming the solid parts and empty space where the holes would be. These aren't metaphors. These are the actual predicted structures of matter at these densities. And here's the wildest part. This pasta layer might be the strongest material known to science, over 10 billion times stronger than steel. If you somehow managed to forge a bridge out of neutron star pasta, it would withstand practically anything short of a black hole's hug. You could hang entire planets from it, and it wouldn't bend. You could smash it with a cosmic sledgehammer, and it wouldn't crack. It is quite literally the ultimate construction material. Of course, you can't actually get any, and if you could, it would probably kill you instantly. But the point stands. This is not just exotic. This is matter at its absolute limit, squeezed and shaped by forces so extreme that it stops behaving like anything we've ever encountered and starts behaving like something out of a fever dream. And yet, for all its strangeness, the pasta layer is real. It's there deep inside every neutron star, sitting quietly between the crust and the core, holding secrets we're only beginning to understand. It's a reminder that the universe doesn't care about our intuitions. It doesn't care if something sounds ridiculous or impossible. If the physics allows it, it happens. And if it happens, we get to study it, marvel at it, and occasionally name it after food. So, the next time you twirl spaghetti on your fork or layer lasagna in a dish or bite into a piece of gnocchi, take a moment to remember, somewhere out there in the heart of a neutron star, matter is arranged in exactly the same shapes, only denser, stranger, and far, far more powerful. Moving inward, we reach the outer core. This is where things go from weird to our best guess. The density here is higher than anything you can create in a lab, so physicists rely on models, math, and the occasional prayer. Welcome to the outer core. This is where things go from weird to our best guess, because no laboratory on Earth can replicate these conditions. No particle accelerator can reach these pressures. No computer can fully simulate what happens when you squeeze matter this tightly. All we can do is observe, calculate, and wonder. And what we think exists here is something truly extraordinary, a superfluid. Most agree that the outer core is made of a superfluid of neutrons, meaning the neutrons flow without friction. Imagine a liquid that flows forever, never slowing down, never settling, never clumping. A fluid so smooth that if you stirred it, it would spin in perfect silence forever. That's not an exaggeration. That's what a superfluid is. In ordinary liquids, atoms and molecules bump into each other constantly. This creates friction, which dissipates energy as heat. That's why, if you stir your tea and then let go of the spoon, the swirling eventually stops. The friction slows it down until the liquid is still again. But in a superfluid, there is no friction. None. The neutrons move past each other without resistance flowing in perfect coordination. If you could somehow reach into a neutron star's core and give the superfluid a gentle push, it would start moving, and it would never stop. Not in a million years, not in a billion. It would flow forever, carrying its motion forward through time without losing a single drop of energy. It's a kind of immortality in a way, a liquid that remembers every push, every stir, every disturbance, and carries it forward indefinitely, silent, eternal, perfect. But the superfluid isn't alone down there. The outer core might also contain protons and electrons, although the protons would be in a superconducting state, allowing electric current to flow without resistance. Think about that for a moment. Not only is the neutron fluid frictionless, but the protons might be conducting electricity without losing any energy. It's like the entire core is a perfect machine operating at maximum efficiency, with no waste, no heat, loss, no slowdown, just pure, uninterrupted motion. These particles interact in ways that give rise to some of the neutron star's more exotic behaviors, like pulsar glitches, sudden changes in rotation that we'll get into in a moment. For now, just imagine a star with the hiccups, and you're halfway there. But here's where the superfluid becomes even stranger. It doesn't rotate the way ordinary liquids do. When you spin a glass of water, the entire liquid rotates together. The water near the edge moves faster than the water in the center, but is all part of one smooth, continuous motion. You can see the swirl. You can feel the drag. Not so with a superfluid. A superfluid doesn't spin smoothly. Instead, it forms tiny discrete whirlpools called quantized vortices. Each vortex carries a fixed amount of angular momentum, a quantum of rotation, and they arrange themselves throughout the fluid like little tornadoes frozen in place. Picture it. Deep inside a neutron star, the superfluid core is filled with these vortices, spinning silently, each one a miniature cyclone of neutrons. They don't merge. They don't spread out. They exist as individual quantized units of spin, all aligned, all rotating in perfect unison. And here's the crucial part. These vortices can pin themselves to the crust. They anchor to the solid outer layer like tiny hooks, catching on the walls of a container. As long as they're pinned, the superfluid and the crust rotate together, locked in sync. But the crust is slowing down, very, very slowly. Due to radiation and magnetic drag, the neutron star's rotation decreases over time. The crust spins a little slower. The magnetic field pulls a little harder. Energy is lost, but the superfluid, it doesn't care. It has no friction, remember, so it keeps spinning at its original speed, locked in by the vortices that are still pinned to the crust. The tension builds. The difference in rotation between the crust and the superfluid grows larger and larger, like winding up a spring. Eventually, something's got to give. The vortices unpin, all at once. In a fraction of a second, the stored angular momentum transfers from the superfluid to the crust. The crust suddenly speeds up just a tiny bit, a few parts in a million, but enough for astronomers to notice. The star glitches. Its rotation jumps. Its pulses arrive a little earlier than expected. It's a cosmic slip-and-release mechanism, like popping the lid off a tightly wound jar. Only instead of peanut butter, it's nuclear matter and space-time. For now, just imagine a star with the hiccups. That's what a pulsar glitch is, a sudden, involuntary spasm deep inside the core. caused by the strange physics of superfluidity and quantized rotation. It's fascinating, it's bizarre, and it's one of the only ways we can peer into the interior of a neutron star without actually going there. Because remember, we can't recreate this in a lab. We can't build a superfluid ocean of neutrons on Earth. We can't compress matter to these densities, hold it together, and watch what happens. The pressures are too high. The forces are too extreme. We simply don't have the tools. So, we observe. We measure the timing of pulsars. We watch for glitches. We build models and run simulations and compare them to the data. And slowly, piece by piece, we assemble a picture of what's happening inside these stars. It's like trying to understand the inside of a locked box by listening to the sounds it makes when you shake it. You can't see inside, you can't open it, but you can infer, deduce, and gradually build a theory of what's in there. And what we've inferred is extraordinary: a frictionless ocean of neutrons, superconducting protons, quantized vortices spinning in silence, all of it hidden beneath kilometers of crust, compressed to densities that shouldn't exist yet do. The outer core is a window into extreme physics, a natural laboratory where matter behaves in ways we've never seen before and may never see again. It's a place where quantum mechanics meets gravity, where the very small and the very large collide, and where the universe shows us just how strange it can be, all from a safe, respectful distance. Because getting close would be unwise. Getting close would be fatal. But from here, billions of kilometers away, we can watch, listen, and learn. We can piece together the puzzle one glitch at a time, one calculation at a time, one observation at a time. And what we're learning is this: neutron stars are not just dense, they're not just heavy, they're not just strange. They are laboratories for physics we don't yet fully understand. They are testing grounds for theories we're still developing. They are windows into the fundamental nature of matter itself. And the deeper we go, the stranger it gets. Finally, we come to the inner core. And this is where things go delightfully speculative. For now, just imagine a star with the hiccups. Finally, we come to the inner core, and this is where things go delightfully speculative. Because at these densities, several times higher than the density of an atomic nucleus, neutrons themselves might not be able to hold themselves together. They may buckle under the pressure, they may dissolve, and when they do, they break down into their fundamental components. Quarks. Quarks are the building blocks of protons and neutrons. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. In ordinary matter, quarks are always bound together, in groups. They don't exist freely on their own. The strong nuclear force keeps them locked inside protons and neutrons, and no amount of pulling or prodding will separate them under normal conditions. But inside a neutron star's core, things are not normal, not even close. At the crushing densities found here, neutrons may no longer be able to maintain their structure. The pressure may be so great that the quarks inside them are liberated, set free from their neutron prisons. And when that happens, you get something entirely new: quark matter. This hypothetical substance is sometimes referred to as quark-gluon plasma, a state of matter where quarks and gluons, the particles that hold quarks together, float freely in a dense, chaotic soup. It's a state that may have existed in the first microseconds after the Big Bang, when the universe was hot and dense enough that quarks hadn't yet combined into protons and neutrons. As the universe expanded and cooled, those quarks came together, forming the ordinary matter we see today. But deep inside a neutron star, we may find a return to that primordial chaos, a place where matter exists as it did in the earliest moments of the universe, before atoms, before nuclei, before anything we would recognize as stable. It would represent an entirely new state of matter, never observed in a lab, only hinted at by cosmic observations and theoretical models. A state where the rules are different, where particles behave in ways we've never seen, and where the boundary between what we know and what we can only guess becomes impossibly thin. And if quarks are freed in the core, they might not stop at just up and down quarks. There's a third type strange quarks, heavier than up and down, and normally unstable, but under the extreme pressure of a neutron star's core, strange quarks might become stable. And if that happens, you get strange quark matter, or more ominously, strange matter. Strange matter is a hypothetical form of matter where up-down and strange quarks coexist in a stable configuration. Some physicists believe that strange matter might actually be more stable than ordinary nuclear matter. And if that's true, it could have some wild consequences. For example, there's a theory that if a single droplet of strange matter, sometimes called a strangelet, were to come into contact with ordinary matter, it might convert it into more strange matter. Like a subatomic zombie infection, one strangelet could in theory begin converting everything it touches, turning entire stars or planets into strange matter. That sounds terrifying, but don't panic. There's no evidence that strangelets are on the loose. No observations of stars suddenly transforming into strange matter. No signs of runaway conversion events tearing through the galaxy. And even if strangelets do exist, they're likely confined to the cores of neutron stars, held in place by gravity, unable to escape. But it's a fascinating idea, and one that pushes the boundaries of what we understand about the stability of matter. Because if strange matter is more stable than ordinary matter, then in some sense, everything we see around us, the atoms that make up planets, stars, and people, might be metastable. Stable for now, but not the lowest energy state, not the final form. It's unsettling, but also oddly beautiful. The idea that the universe might have multiple solutions, multiple stable configurations of matter, and that we just happen to live in one of them. Of course, strange matter isn't the only exotic possibility lurking in the inner core. There are other candidates, other particles that might exist at these densities. One such particle is the hyperon. A hyperon is similar to a neutron, but with an additional strange quark mixed in. They're heavier than neutrons and tend to decay quickly under normal conditions. But inside a neutron star's core, they might stick around. They might play an important role in the structure and behavior of the star. Why does this matter? Because the composition of the star's core determines how it behaves, how much mass it can hold before collapsing into a black hole, how it responds to pressure, how it emits radiation. If the core is made entirely of neutrons, there's a certain set of rules. If it's made of quark matter or hyperons, those rules change. It's like trying to predict how a cake will rise without knowing whether it's made of flour or foam. the ingredients matter, and we don't yet know what the ingredients are. Some scientists even think that quark stars could be a separate class of objects entirely. These hypothetical stars, smaller and denser than neutron stars, would be made entirely of quark matter. They might form when neutron stars collapse further, but don't quite become black holes. If quark stars exist, they'd be even more extreme than neutron stars, with surface conditions that defy imagination. Detecting one, however, is tricky. From far away, a quark star might look very much like a neutron star. It might pulse, it might spin, it might emit X-rays or gamma rays, but subtle differences, like how quickly it cools or how it reacts during a collision, could reveal its true identity. Future telescopes and gravitational wave detectors may be able to spot these differences and help confirm whether quark stars are real or whether they're just a theoretical curiosity, a possibility allowed by the math, but not realized in nature. And then because the universe loves to keep us guessing, there are even more speculative ideas. Some physicists propose that dark matter, the mysterious invisible substance that makes up most of the mass in the universe, might accumulate inside neutron stars. Over time, this dark matter could alter the star's behavior or even trigger its collapse into a black hole. Others suggest that neutron stars might contain Bose-Einstein condensates, pion condensates, or kaon condensates, all exotic forms of matter that we don't fully understand, but suspect might occur under the right conditions. It's like neutron stars are playgrounds for every weird theory physics has ever invented. They sit at the crossroads of gravity, quantum mechanics, particle physics, and nuclear science, pushing each field to its limits and demanding answers to questions we're barely able to ask. And here's the most incredible part. We may be on the verge of finding out. New observatories, like the NICER instrument aboard the International Space Station, are measuring neutron stars with unprecedented precision, trying to pin down their exact size and mass. These measurements help determine the equation of state, the relationship between pressure and density inside a neutron star, which in turn reveals what kind of matter they contain. Meanwhile, gravitational wave detectors like LIGO and Virgo are capturing the signatures of neutron star mergers. These waveforms encode detailed information about how neutron stars deform and bounce during collisions, offering clues about their internal structure. All of this means we're inching closer to answers to questions like, what is the most stable form of matter? How does the universe behave under maximum pressure? What's hiding inside the densest objects that aren't black holes? Neutron stars don't just stretch our imagination, they stretch our theories. They reveal the limits of our understanding and point toward the mysteries still to come. And as we continue to study them, we may discover not just what neutron stars are, but what we are made of and what the universe might still become. Because in the end, strange matter, quark stars, and hyperon cores aren't just strange for the sake of it. They are possibilities, whispers from the edge of known physics, waiting for someone to listen closely enough to hear them clearly. Some scientists even think that quark stars could be a separate class of objects entirely. If quark stars exist, they'd be even more extreme than neutron stars. Standing on the surface of a neutron star, is not something you'd want to try. And not just because the travel arrangements are a bit inconvenient. The real issue is that physics itself becomes uncooperative the closer you get. Gravity, time, space, all the familiar rules begin to stretch, bend, and in some cases, politely step aside while something stranger takes over. This chapter is all about what it means to exist near a neutron star, a place where gravity is so strong and space-time so warped that even light starts to question its life choices. Let's start with gravity, since that's the main character here. Gravity on the surface of a neutron star is, to put it mildly, intense. If you are somehow able to survive long enough to stand on it, which for the record you would not, you would weigh more than 200 billion times what you do on Earth. That's a 2 followed by 11 zeros. If you weigh 70 kilograms, here on Earth, you would weigh about 14 quadrillion kilograms on a neutron star. You would be pressed down with such force that every atom in your body would be crushed beyond recognition before you could even think about saying, ouch. Your bones would collapse, your organs would liquefy, your very molecular structure would cease to exist in any meaningful sense. You wouldn't just die, you'd be atomically obliterated. But even though you can't visit one, we can still imagine what it would be like. The escape velocity, the speed you need to break free of a planet's gravity, is also completely unhinged. On Earth, escape velocity is about 11 kilometers per second. That's why rockets are so large and require so much fuel. They're fighting gravity every inch of the way up. On a neutron star, it's around 150,000 kilometers per second. That's more than half the speed of light. If you wanted to launch a rocket from a neutron star surface, you'd need fuel tanks the size of planets. And even then, the rocket would probably melt before it got out of the gravity well. The energy requirements are so extreme that it borders on the physically impossible. This immense gravity doesn't just hold on to matter, it also messes with light. When light tries to leave the surface of a neutron star, it has to climb out of an extremely steep gravitational well. As it does, it loses energy and shifts toward the red end of the spectrum. This effect is called gravitational redshift, and it means that if you were standing at a safe distance, looking at the light coming from a neutron star, it would appear redder and less energetic than it actually is. The star isn't changing color. Space-time is. Imagine you're at the bottom of a deep canyon, shouting up to someone standing at the top. By the time your voice reaches them, it sounds lower, deeper, because the sound waves have been stretched by the effort of climbing out. Gravitational redshift works the same way, only with light instead of sound. A photon that leaves the surface as blue light might arrive at your telescope as red light, or infrared, or something even less energetic. The photon hasn't changed, it hasn't slowed down, but it's lost energy fighting against gravity, and that energy loss shows up as a change in wavelength. This is not a small effect, it's measurable, significant, and it tells us something profound about the nature of space-time itself. Gravity isn't just a force pulling things together. It's a distortion in the fabric of reality, bending light, warping space. And even here's where it gets truly strange, altering the flow of time. This warping of space-time has another effect too. Time itself runs differently near a neutron star. The stronger the gravitational field, the slower time moves. This is a prediction of Einstein's general theory of relativity, and it's been tested and confirmed many times. On Earth, we have to correct for this time dilation when using GPS satellites. The satellites orbit high above the planet, where gravity is slightly weaker, so their clocks run slightly faster than clocks on the ground. The difference is tiny, just a few microseconds per day, but it's real. And if we didn't account for it, GPS wouldn't work. But near a neutron star, the effect is magnified to an almost surreal degree. If you could float just above the surface of a neutron star and somehow survive, time for you would pass more slowly than it would for someone far away. A minute for you might be several minutes for them. An hour for you might be several hours for them. Over longer periods, this difference could be dramatic. A person spending what feels like a few years near a neutron star could return to find decades have passed elsewhere. It's not quite time travel, but it's the next best thing. You're not jumping forward into the future. You're not reversing the past. You're simply experiencing time at a different rate. Your clock ticks more slowly. Your heartbeat stretches out. Every second you experience is longer subjectively identical to you, but objectively extended when compared to someone far from the gravitational field. And this isn't science fiction. This isn't speculation. This is what happens when you take Einstein's equations seriously and apply them to an object as dense as a neutron star. Time dilates, clocks slow, reality bends. And that's just what's happening to time and light. Space itself is distorted too. The intense gravity curves space so dramatically that objects behind the star can actually be seen around its edges. This phenomenon is called gravitational lensing, and it means that a neutron star, despite being tiny, can appear much larger than it actually is, like a funhouse mirror held up to the cosmos. The star's gravity acts like a magnifying glass, bending the paths of light rays and letting us see otherwise hidden regions of space behind it. If there were a bright spot on the far side of the star, you'd still be able to see it distorted and stretched around the edge, the light taking a curved path to reach you. This isn't an illusion. This isn't a trick of perception. This is space-time itself, being warped by mass. The light is genuinely traveling along a curved path because the space through which it's moving is curved. Imagine a trampoline with a heavy ball in the center. The fabric dips down, creating a bowl-shaped depression. If you roll a marble across the trampoline, it won't travel in a straight line. It'll curve toward the ball, following the shape of the depression. That's what gravity does to space. And near a neutron star, the depression is so deep that light itself is forced to take a detour. The result, you can see more than half of the neutron star's surface at once. The horizon curves upward. Light from the far side bends around, reaching your eyes from angles that shouldn't be possible. It's as though you're peeking around a corner that doesn't exist, seeing a view that defies geometry. These strange distortions make neutron stars incredibly useful for scientists. By observing the way light and time behave around them, physicists can test theories of gravity, probe the behavior of matter under extreme conditions, and explore the frontiers of astrophysics, all from a safe, respectful distance. Now let's imagine a thought experiment, just for fun and with zero risk of injury. Imagine you're in a specially designed space pod, the kind that ignores most known laws of physics for narrative convenience. You're floating just a few hundred kilometers above the surface of a neutron star. Outside your pod, the star stretches below you, a perfectly spherical orb about 20 kilometers wide. It's not bright in the usual sense, but it's hot, incredibly hot. The surface temperature could be over 1,000,000 degrees Kelvin, though. Some older neutron stars cool down to just a few 100,000. Looking out the window, you'd notice something unusual. The horizon curves upward sharply. You can see more than half of the star at once, thanks to gravitational lensing. If the neutron star had a glowing patch on its far side, you'd still be able to see it peeking around the edge, the light taking a curved path to reach you. At a safe altitude, your ship holds position. Below you, the neutron star is rotating. Some of them spin slowly once every few seconds. Others, especially millisecond pulsars, spin hundreds of times per second. If this one is on the faster end, the entire surface might be whirling beneath you, like a compact record player, flickering with beams of radiation sweeping through space like a lighthouse. Your onboard clock is ticking, but something feels off. And it is. Time inside the pod ticks more slowly compared to time back on Earth. Your watch still works, but when you compare notes with mission control later, you'll find that your few hours up here translated to several hours or even days down there. You've effectively skimmed through time, like skipping a stone across a pond made of gravity. Outside magnetic fields swirl with unimaginable strength. Your sensors are struggling to stay calibrated. A typical neutron star already has a magnetic field trillions of times stronger than Earth's. If you're near a magnetar, that number could climb into the quadrillions. The field is so strong, it could distort the shape of atoms. Even with shielding, your ship's electronics are flickering, twitching, and occasionally showing system alerts that you prefer not to read right now. But you're curious. What lies beneath that crust? You aim an imaginary probe toward the surface. It dives through the outermost layer, just a few centimeters thick, where plasma and radiation swirl in a violent mix. Below that is the solid crust made of tightly packed nuclei, surrounded by a sea of electrons. A little deeper, and things begin to change. The pressure grows so immense that electrons are crushed into protons, forming neutrons. These neutrons start to drip out of the nuclei and form a dense, neutron-rich fluid. Then comes the famous nuclear pasta layer, where matter is squished into strange shapes, rods, sheets, blobs. It's nuclear matter, behaving like cooked spaghetti. And beneath that, the superfluid core, neutrons flowing without resistance, a quantum liquid that carries heat and spin in ways we don't fully understand. At the very center, maybe something stranger still, a core of quark matter, or something else we haven't imagined yet. But back on the surface, it's eerily calm. There are no sounds in space, but you imagine the silence would feel louder here. Not emptiness, but compression, like the weight of the entire star pressing in on itself. Occasionally, the star might glitch, a sudden spin-up caused by a shift deep inside, a tiny hiccup in its perfect rhythm. You wouldn't see it, but your instruments, would pick it up instantly. A jolt in the regularity of the pulses, a twitch in the star's posture. You spend a few more moments in orbit, letting the reality of this place sink in. A teaspoon of this matter would weigh more than Mount Everest. The gravity is so strong that time warps. The interior is made of matter in states not seen anywhere else in the universe, and yet it's just sitting there, stable, quiet, spinning in the dark. Eventually, you pull away. The star shrinks in your viewport. It was never very big, but now it looks like just another speck in the blackness, still pulsing, still whispering. As you accelerate into the distance, your clocks slowly resynchronize with Earth time. Messages start to catch up with you. The familiar rhythms of home return. But something is different now. You've seen a place where physics is stretched to its limits, where matter folds in on itself, where gravity becomes a sculptor, and time flows like syrup. You've looked into the eye of a collapsed sun and returned. Of course, all of this is just imagination. In reality, no pod could survive that close. No human could endure the radiation, the pressure, the temperature. But even at a safe distance, neutron stars exert their influence. They pull at our equations, our telescopes, our imaginations. They show us what happens when the universe pushes matter to its limits and asks, "What now?" And what happens is astonishing. Space bends, time slows, atoms surrender, and something stable, silent, and endlessly strange is left behind. Neutron stars remind us that the cosmos doesn't need to be large to be powerful, that the tiniest points of light can hide the deepest wells of gravity, and that even in collapse, the universe creates something remarkable. And when they spin, they don't just sit quietly like cosmic pebbles. They flash, they blink, they beam. When neutron stars spin, they don't just sit quietly like cosmic pebbles. They flash, they blink, they beam. And from across the galaxy, we see these pulses with the regularity of a ticking clock. That's why we call some neutron stars pulsars, short for pulsating radio source. But don't let the name fool you. These aren't flickering candles. They are the lighthouses of the universe, and their beams are powered by some of the most extreme physics imaginable. Let's rewind for a moment. When a massive star collapses into a neutron star, it doesn't just shrink, it spins. This is due to a principle in physics known as the conservation of angular momentum. It's the same effect you see when a figure skater pulls in their arms and spins faster. As the mass of the star collapses inward, its rotation speeds up dramatically. A star that originally took days to rotate once may now spin dozens or even hundreds of times per second. That might sound fast, and it is. But the truly mind-bending part is how stable this spin can be. Pulsars rotate with astonishing precision. Some of them keep time better than the most accurate atomic clocks on Earth. If you had a pulsar on your wrist, ignoring the small matter of it weighing more than the moon, you could tell time more reliably than with anything humans have ever built. The pulses arrive with such regularity that astronomers can predict them years in advance, down to fractions of a millisecond. They're cosmic metronomes, ticking away in the darkness, never missing a beat. It's almost unsettling, really. Something so violent in its birth, so extreme in its nature, and yet so perfectly reliably steady. Now, not every neutron star is a pulsar. To be a pulsar, a neutron star has to meet two conditions. It needs to have a strong magnetic field, and it needs to be spinning at a decent clip. The combination of spin and magnetism creates a powerful electric field which rips charged particles from the surface and accelerates them along the magnetic poles. These charged particles emit beams of electromagnetic radiation, usually in the radio spectrum, though sometimes in visible light X-rays or even gamma rays. But here's the key. The magnetic axis is usually not aligned with the rotation axis. Imagine a spinning top with a flashlight taped to its side, not quite pointing straight up. As the top spins, the beam of light sweeps around in a circle. That's essentially what's happening with a pulsar. The neutron star spins, and its magnetic poles, where the beams of radiation shoot out, sweep through space like the light from a lighthouse. And if one of those beams happens to cross Earth, we see it as a regular pulse. Flash, 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 like a cosmic blink, timed to perfection. The neutron star itself isn't turning on and off. It's always emitting radiation. But from our perspective, we only see the beam when it's pointing at us. The rest of the time, it's sweeping past invisible, lighting up other parts of the galaxy that we'll never see. The first pulsar ever discovered was found in the late 1960s by Jocelyn Bell Burnell, who at the time was a graduate student working on a radio telescope. She noticed a regular repeating signal, a pulse occurring every 1.3 seconds. It was so regular, in fact, that the team briefly considered the possibility of it being an artificial signal. They jokingly labeled it LGM-1, short for Little Green Men. But soon other similar signals were found, and the true nature of pulsars began to emerge. No aliens, just very, very punctual dead stars. That first pulsar still spins today like a heartbeat frozen in time, and we've since found thousands more each with its own rhythm and personality. Some pulsars spin slowly once every few seconds. Others, known as millisecond pulsars, spin hundreds of times per second. The fastest one known spins over 700 times per second. 700. Let that sink in for a moment. Imagine something the mass of the sun compressed into a sphere 20 kilometers wide, spinning around 700 times every single second without flying apart. The only reason it holds together is because of its immense gravity. If a neutron star were any less dense, it would tear itself to pieces. The equator of a millisecond pulsar is moving at a significant fraction of the speed of light. The surface is whipping around so fast that matter itself is barely holding on, and yet it spins. Stable, steady, precise. Millisecond pulsars are particularly interesting because many of them are thought to have been recycled. That is, they were once ordinary pulsars that slowed down over millions of years. But then they picked up some extra speed by stealing matter from a nearby companion star. As material spiraled onto the neutron star, it transferred angular momentum, like pushing a merry-go-round, and the neutron star spun faster and faster. These cosmic vampires have an eerie elegance to them, sipping from their neighbors, silently accelerating to ridiculous speeds, taking what they need and spinning on. It's a slow process spanning millions of years. But eventually, the neutron star is spun back up, rejuvenated, brought back from the dead, so to speak, and it becomes a millisecond pulsar, flashing faster than the eye can see, invisible to us, invisible light, but blazing in radio waves, a beacon across the cosmos. Despite their terrifying density and incredible power, pulsars are surprisingly useful. Astronomers use them as natural cosmic clocks. By measuring the arrival time of their pulses, we can detect incredibly subtle phenomena, like the tiny wobbles caused by orbiting planets, or the stretching of space-time itself due to gravitational waves. There's even been talk of using pulsars for spacecraft navigation. Imagine future explorers traveling through deep space using a map made of dead stars to guide their way. No GPS satellites, no ground stations, just the ancient, reliable pulses of neutron stars ticking away in the dark, marking time and space with perfect precision. Some pulsars have companions white dwarfs, or even other neutron stars, and orbit around them in tight, complicated dances. These systems are especially valuable because their gravitational interactions reveal a wealth of information. For example, the famous Hulse-Taylor binary pulsar provided the first indirect evidence for the existence of gravitational waves. As the two neutron stars orbited each other, they slowly spiraled inward exactly as predicted by Einstein's general theory of relativity. The system lost energy not through light, but through ripples in spacetime. That discovery earned a Nobel Prize and paved the way for the gravitational wave detectors we use today. And then there are pulsar glitches. Every now and then, a pulsar that's been spinning steadily for thousands of years will suddenly speed up just a little. These glitches are thought to be caused by starquakes, shifts in the rigid crust of the neutron star, or by interactions between the superfluid interior and the solid outer layers. Whatever the cause, it's like the neutron star stumbles and quickly recovers slightly faster than before. A cosmic hiccup, if you like. Pulsars also play a role in some of the most violent events in the cosmos. When two neutron stars spiral into each other and merge, a process that takes hundreds of millions of years, they can produce a burst of gravitational waves, a brief flash of gamma rays, and a kilonova explosion. These are rare events, but when they happen, they light up the universe and create heavy elements like gold and platinum. The death of pulsars can quite literally result in treasure. But perhaps the most astonishing thing about pulsars is just how calm they are. On paper, they are absurd. City-sized spheres of degenerate matter spinning at hundreds of revolutions per second, radiating energy through immense magnetic fields and pulsing across the galaxy. And yet from Earth, they arrive as steady, soothing beacons, like metronomes, keeping time in the vast silence of space. Some emit pulses that are so regular, we can predict their timing to within a millionth of a second. They remind us that even in the chaotic dance of galaxies and dark matter, there are rhythms, reliable patterns, quiet pulses in the dark. In a way, they're the perfect bedtime companions, not noisy or explosive, just gently persistent. A tap, a beat, a flicker in the night sky. You may never see one with your eyes. You may never hear its call. But out there across the emptiness, a neutron star is spinning, always, just as it has for millions of years, and just as it will for millions more. Tick, tick, tick. Despite their terrifying density and incredible power, pulsars are surprisingly useful. They're natural cosmic clocks. And then there are pulsar glitches. Neutron stars may appear still from a distance, those steady pulses, those elegant spins, but on the inside, they're anything but calm. Beneath the crust, deep inside these cosmic pressure cookers, something stirs, something shifts, and every so often, it causes the star to twitch. A sudden change, a momentary hiccup in the rhythm of the universe. These strange interruptions are called glitches, and they are the result of forces so exotic they might as well be from science fiction. But before we dive into the strange world of neutron star glitches and starquakes, let's take a moment to appreciate just how remarkably steady these stars normally are. Pulsars, the spinning neutron stars that beam radio waves toward Earth, are famously reliable. Some of them rotate hundreds of times per second, with such consistency that astronomers use them as cosmic clocks. In fact, a few pulsars are so regular that if you compared their pulses to an atomic clock, the differences would be measured in microseconds over years. They are quite literally some of the most precise timekeepers in the universe. But every now and then, the pulse skips a beat, or rather, it doesn't skip, it speeds up. Ever so slightly, the star's rotation rate increases. Not by much usually, just a few parts in a million, but it's enough for astronomers to notice. It's enough to raise questions. Because in the universe, objects that spin are supposed to slow down over time. Friction radiation and magnetic drag all act to gradually reduce the rotational speed of neutron stars. So when one speeds up even slightly, something strange is happening. These sudden speed-ups are called pulsar glitches. They were first discovered in the late 1960s when astronomers noticed that the Vela pulsar, a young neutron star about 1,000 light-years away, suddenly began spinning slightly faster. And since then, similar events have been observed in dozens of other pulsars. So, what's going on? To understand glitches, we have to take a peek beneath the crust of the neutron star. Now, this crust isn't like the one under your feet. It's far stronger, far denser, and under pressures billions of times greater than anything on Earth. But even this supercrust has limits. Over time, as the star spins and its internal dynamics shift, stress builds up in the crust, especially in the region where it connects to the star's inner layers. Eventually, something's got to give. One possible cause of a glitch is a starquake. Just like Earth has earthquakes, neutron stars can experience sudden shifts in their crusts. The intense pressure causes a crack, a break, or a sudden rearrangement. The crust snaps ever so slightly inward, and because this shifts mass closer to the axis of rotation, the star speeds up like a spinning ice skater pulling in their arms. The rotation rate increases, and the pulses arrive just a little earlier than expected. It's a tiny shift, a subtle change, but in the precision world of pulsar timing, it's unmistakable. Another explanation, one that digs deeper, involves the superfluid interior of the neutron star. Beneath the crust lies a layer of neutron-rich superfluid, a bizarre state of matter that flows without any resistance. It's frictionless, silent, and very, very particular about how it behaves. This superfluid doesn't spin in the normal way. Instead, it forms tiny whirlpools called quantized vortices, each carrying a tiny bit of angular momentum. These vortices anchor themselves to the crust, but over time, they can get pinned in place. As the outer crust slows down from radiation loss, the inner superfluid keeps spinning at its original speed. The tension between these two layers builds like winding a spring. Eventually, the vortices unpin all at once. In a fraction of a second, the stored angular momentum transfers to the crust, causing the star to spin slightly faster. And just like that, a glitch occurs. It's a cosmic slip and release mechanism, like popping the lid off a tightly wound jar. Only instead of peanut butter, it's nuclear matter and space-time. Both models, crustal starquakes and superfluid vortex unpinning likely, play roles in different kinds of glitches. Younger neutron stars, which tend to glitch more often, might be more prone to crustal shifts. Older, cooler neutron stars may experience more superfluid dynamics. The truth is, we're still learning. Glitches are one of the only windows we have into the deep interiors of neutron stars. Every one we detect is a clue. What makes these glitches even more fascinating is how quickly the star recovers. After a glitch, the spin rate doesn't just stay at its new value forever. It usually relaxes, slowly drifting back toward the pre-glitch rate over days, weeks, or even months. The star's interior seems to remember its original rhythm and tries to get back to it like a music box winding down. And here's a curious thing. Sometimes the glitch is accompanied by changes in the star's pulse profile, the shape of the beam we see from Earth. That suggests that something more than just rotation is shifting. Maybe the magnetic field is twitching. Maybe the crust is deforming. Maybe the whole star is subtly rearranging itself in a process we still don't fully understand. There's something deeply poetic about that, isn't there? A star, a dense remnant of something long dead, still capable of shifting, of quaking, of changing. Not just a frozen relic, but a living machine full of tension and movement, creaking under the strain of its own existence. Glitches aren't just a curiosity. They have practical uses too. By studying the timing of glitches, scientists can learn about the structure of neutron stars, things like the strength of their crusts, the behavior of superfluid matter, and even the configuration of their internal magnetic fields. It's like watching a cracked bell ring and learning everything about the metal inside from the sound it makes. And then there's the rarest, most mysterious kind of glitch, the anti-glitch. Instead of speeding up, the neutron star suddenly slows down. This has only been observed a handful of times, and we're still not quite sure what causes it. Perhaps a magnetic field reconfiguration, or a sudden change in the interaction between the crust and the superfluid. Whatever it is, it's another reminder that neutron stars are full of surprises. They may seem like cosmic clockwork from a distance blinking, in perfect time spinning with robotic regularity. But inside, they're full of stress tension and sudden jolts. They creak, they twitch, they remember, they adjust. It's strange to think of stars having such personalities. Yet the more we study them, the more we realize that neutron stars are not just extreme, they're expressive. Their glitches and quakes are like sighs from something ancient and immense, whispering through the vacuum of space. And so, we watch, we listen, we wait for the next tiny tremble from a star that spins in silence, carrying the memory of its collapse and the weight of forces we're only beginning to understand. There's something deeply poetic about that, isn't there? A star, a dense remnant of something long dead, still capable of shifting, of quaking, of changing. But some neutron stars go even further. Some neutron stars, as if being dense, tiny, and wildly fast, weren't enough go even further. They take their already extreme properties and crank them up into the realm of the ridiculous. These are the magnetaires, neutron stars with magnetic fields so powerful they make ordinary neutron stars look like fridge magnets. In a universe full of wild phenomena, magnetars are the ones that leave even seasoned astrophysicists blinking in quiet awe. To understand what makes magnetars so special, let's begin with the basics of magnetism. Every neutron star has a magnetic field. It's a byproduct of the star's rotation and the way charged particles move within and around it. Even a typical neutron star, the normal kind, might have a magnetic field trillions of times stronger than Earth's. That's already enough to cause problems for anything that might wander too close. But magnetars take this to an entirely different level. Their magnetic fields can be over 1,000 times stronger than those of regular neutron stars. In numbers, we're talking about magnetic fields of around 1 quadrillion Gauss. That's a 1 followed by 15 zeros. Earth's magnetic field, for comparison, is around half a Gauss. So, a magnetar's field is not just strong, it's borderline absurd. It's so strong that if one were placed at a distance equal to the moon, it could erase your credit card. That's not poetic exaggeration. That's just physics being terrifying. The magnetism of a magnetar is so intense that it affects the very fabric of the vacuum around it. In these fields, quantum electrodynamics kicks in, and the vacuum becomes birefringent, a fancy way of saying that empty space starts to behave like a lens-bending light differently depending on its polarization. This has actually been observed by astronomers looking at the light from a known magnetar, confirming that these effects are not just theoretical musings, but real phenomena happening hundreds or thousands of light years away. So, how do magnetars form? The current thinking is that they are born from especially massive stars that collapse with an unusually rapid spin and a particularly high internal magnetic field. During the core collapse, as the star's volume shrinks dramatically, magnetic field lines are compressed like winding up a coil. This amplifies the magnetic field to monstrous levels. The result is a magnetar, a dense, spinning neutron star with a magnetic field that could tear apart atoms from a distance. But here's the interesting twist. Magnetars don't spin very fast for long. Their intense magnetic fields create strong drag forces which quickly slow their rotation. Most magnetars spin only once every few seconds, sluggish by neutron star standards. That's still faster than your average turntable, of course, but much slower than millisecond pulsars. The energy they lose through magnetic braking gets dumped into their surroundings, heating the star's surface and fueling bursts of high-energy radiation. And that's where things get really dramatic. Magnetars are known for their outbursts, sudden intense flares of X-rays and gamma rays. These flares can release more energy in a single second than the sun emits in 100,000 years. Some of them are so powerful that they can be detected across the entire galaxy. Others are more subtle, soft gamma ray repeaters that flare quietly, like a sleeping dragon occasionally snorting fire. The most powerful magnetar flare ever recorded happened on December the 27th, 2004, from a magnetar about 50,000 light years away. For a fraction of a second, it was the brightest thing in the sky, aside from the sun. If that flare had happened within 10 light years of Earth, it could have seriously damaged our atmosphere. Fortunately, it didn't. Space is big, and magnetars, while dangerous, tend to keep their distance. These outbursts are thought to be caused by starquakes. Yes, you heard that right. Starquakes. Just like Earth's crust can shift and crack during an earthquake, the rigid crust of a neutron star can suddenly snap under the strain of the intense magnetic field. This releases a tremendous amount of energy, often accompanied by a shift in the magnetic field itself. Imagine the crust of a star packed tighter than anything you can imagine, suddenly cracking with a snap that sends ripples through space-time. That's a magnetar starquake. These events are not just fascinating, they're scientifically useful. The energy from magnetar flares travels through space and can interact with other objects. They can trigger reactions in nearby gas clouds, influence star formation, and even give us clues about the structure of space itself. By studying them, astronomers can probe conditions that are impossible to recreate on Earth. Magnetars become, in essence, natural laboratories for high-energy physics and quantum mechanics. One of the strangest things about magnetars is that, despite all their fury, they live relatively short and quiet lives. After about 10,000 years, which in cosmic terms is like the blink of an eye, their magnetic fields weaken their flares, subside, and they begin to fade into the background, becoming more like ordinary neutron stars. Their time in the spotlight is brief, but unforgettable. Astronomers have identified only a few dozen confirmed magnetars, though there are likely many more hidden across the galaxy, too faint or distant for us to detect. Some are found in the aftermath of supernovae. Others sit quietly in star-forming regions, lurking like sleeping giants. We've even detected fast radio bursts, sudden intense bursts of radio waves from deep space that might be linked to magnetar activity. The mystery deepens. Because of their unique characteristics, magnetars sometimes show up in science fiction. They are the villains of neutron star stories, powerful, unstable, and unpredictable. But like many things in the universe, their real story is more nuanced. Yes, they're powerful. Yes, they're dangerous. But they're also surprisingly fragile, cracking under their own magnetic stress, fading quickly compared to their more stable siblings, and spending most of their lives in eerie silence. Imagine being near one. Not too near, of course. From a safe distance of several light years, you might see it as a faint source of high-energy radiation. You wouldn't hear it. But if it flared, you might see a sudden brief spike of light on your instruments. It would flash and fade in less than a second, leaving your sensors buzzing and your software asking, "What was that?" And that's how it goes with magnetars. They arrive with a bang, spin down, with a sigh, and vanish into the night like cosmic ghosts. But in their brief lives, they show us the raw, unfiltered power of the universe. They're a reminder that nature doesn't need size to be terrifying, just density magnetism and the occasional catastrophic temper tantrum. Yet there's something oddly peaceful about them too. After the flares, after the bursts, after the cracks and quakes, magnetars settle. They spin slowly, they cool, they fade, they become quiet again. And somewhere in the galaxy, one of them might be doing just that right now, flaring silently in the darkness, twisting magnetic fields like spaghetti. and bending light itself with a shrug of its magnetic shoulders. Magnetars are not monsters. They are masterpieces, strange, brief, and unforgettable. The most powerful magnetar flare ever recorded happened on December 27th, 2004. For a fraction of a second, it was the brightest thing in the sky aside from the sun. Neutron stars spend most of their lives alone, spinning quietly, flashing their steady pulses into the dark. But sometimes, just sometimes, they find a partner. Another neutron star, perhaps, or a massive star that has yet to collapse. And when these companions orbit close enough, a dramatic fate begins to unfold. Over millions, even billions of years, their orbits shrink, their dance quickens, and eventually the two objects collide. When this happens, the universe doesn't just watch, it celebrates with a spectacular explosion known as a kilonova. Let's walk through how we get there. Imagine two neutron stars orbiting each other. Maybe they were once part of a binary star system, two massive stars that both went supernova and became neutron stars. If they remained gravitationally bound, they would continue orbiting around their common center of mass, gradually spiraling inward. This inward motion is caused by the emission of gravitational waves, ripples in the fabric of space-time itself. Every orbit sends out a little pulse of gravitational energy, stealing just a bit of momentum from the system. Over immense periods of time, these ripples slowly drain energy from the orbit, tightening the spiral. The two stars draw closer and closer. Their orbits quicken. Years become months. Months become days. And eventually, they whirl around each other many times per second, screaming silently through the cosmos. And then they merge. When they do, the result is one of the most extreme events the universe can produce, a cataclysm of density, gravity, and light. The collision of two neutron stars unleashes a flash of gamma rays, a shower of gravitational waves, and a glowing radioactive explosion known as a kilonova. Kilonovae are a special kind of supernova, not quite as luminous as the core collapse explosions that create neutron stars, but vastly more powerful than most other types of stellar outbursts. They shine 1,000 times brighter than a typical nova, hence the name, kilonova. But brightness isn't even the most interesting part. Kilonovae are also factories for the heaviest elements in the universe: gold, platinum, uranium. These don't form in ordinary stars. The nuclear fusion processes inside stars can only build elements up to iron. Anything heavier than that needs extreme conditions, massive energy, dense neutron-rich environments, and rapid neutron capture. And that's exactly what a neutron star collision provides. When the two stars collide, chunks of ultra-dense neutron-rich matter are ejected into space. As this matter cools and expands, it undergoes a process called AR process nucleosynthesis, or rapid neutron capture. In this process, atomic nuclei absorb neutrons faster than they can decay, building up into heavier and heavier elements in just seconds. When the dust settles, what remains is a cloud of newly minted heavy elements drifting through space and eventually becoming part of future stars, planets, and people. Yes, if you're wearing a gold ring or have a bit of platinum in your electronics, that material may very well have been forged in the merger of two neutron stars billions of years ago. Somewhere deep in the universe, a collision happened, and atoms from that explosion eventually found their way to Earth, to your hand, to your phone, to your teeth if you have gold fillings. We've known about this process in theory for a long time, but we didn't have direct evidence of it until 2017. That year, gravitational wave observatories detected a signal named GW17817, a ripple in spacetime caused by the merger of two neutron stars about 130 million light years away. Just seconds later, a burst of gamma rays was detected. Then telescopes around the world sprang into action, looking at the patch of sky where the signal came from. What they found was a faint, glowing object, a kilonova. Over the following days, astronomers observed the light change in brightness and color. As the explosion cooled, the spectral signatures of heavy elements appeared: gold, platinum, lanthanides. It was the smoking gun, direct proof that neutron star mergers create gold, platinum, and other R-process elements. This event was a landmark in modern astronomy. It was the first time we observed the same cosmic phenomenon in multiple ways: gravitational waves, gamma rays, visible, light X-rays, and radio waves. It marked the dawn of what scientists call multi-messenger astronomy, where different kinds of signals combine to tell a more complete story. From GW177, we learned that neutron star collisions are not only incredible fireworks displays, but also vital to the cosmic economy. They're the reason the universe has the ingredients needed to make worlds and everything on them. But kilonovae don't always come from neutron star pairs. Sometimes a neutron star merges with a black hole. In these cases, the results are different, sometimes quieter, sometimes more violent, depending on the size of the black hole and the angle of the collision. If the black hole is too massive, it can swallow the neutron star whole without producing much of a light show. But if conditions are just right, it can tear the neutron star apart, creating a brief but spectacular kilonova. These neutron star black hole mergers are harder to detect, but they offer valuable insights. They tell us about the population of compact objects in the universe, the role of black holes in binary systems, and the limits of neutron star structure before collapse. Every merger is a new chapter in the story of stellar evolution, and a new opportunity to test the boundaries of physics. Even more intriguing, some theorists believe that in the moment two neutron stars merge, they may briefly form a hypermassive neutron star, an object so dense and massive that it can only exist for a fraction of a second before collapsing into a black hole. During that sliver of time, it might emit gravitational waves in complex chaotic patterns, offering us a brief glimpse into the physics of matter at its absolute limits. These moments are fleeting, but they leave a lasting imprint on the universe. The gravitational waves spread outward at the speed of light. The gamma rays race through space. The kilonova glows and fades, scattering heavy elements into the galactic neighborhood. And here on Earth, we detect it. We decode it. We marvel at it. From our little corner of the cosmos, we watch these rare, brilliant collisions and learn about the past, not just the past of distant stars, but our own cosmic ancestry. The iron in your blood, the iodine in your thyroid, the gold in your jewelry. It all began in places like this. Neutron star collisions are not everyday events. In a galaxy like ours, they may only happen once every 10,000 to 100,000 years. But when they do, they are spectacular. They are bright, brief, and full of meaning. They are proof that even in death, stars can give, that even in collision, the universe creates, that something as violent as a neutron-star merger can lead to beauty in the form of precious metals, new elements, and glowing clouds of light. So next time you see gold, or platinum, or any of the rare heavy things we treasure on Earth, take a quiet moment to remember these didn't come from the ground. They came from stars. Not just any stars, but the densest, most extreme remnants of stars locked in a slow, spiraling embrace that ended in a single spectacular kiss. A kiss that shook space-time, a kiss that lit up the universe, a kiss that quite possibly made you. We've known about this process in theory for a long time, but we didn't have direct evidence until 2017. That year, gravitational wave observatories detected a signal, a ripple in space-time caused by the merger of two neutron stars about 130 million light-years away. It was August 17th, 2017. The signal, later named GW1-607, arrived at the LIGO and Virgo detectors, massive instruments designed to catch the faintest tremors in the fabric of space itself. For just under a minute, the detectors recorded the final moments of two neutron stars as they spiraled together, their dance growing faster and faster until they collided. Just seconds later, a gamma ray burst was detected, a brief, intense flash of the most energetic light in the universe. And then, telescopes around the world sprang into action. Radio dishes turned. Optical telescopes pivoted. X-ray satellites adjusted their aim, all pointing to the same patch of sky, a galaxy called NGC 4993 in the constellation Hydra. What they found was a faint glowing object, a kilonova, fading slowly over days and weeks, its light shifting through different colors as the radioactive debris cooled and expanded. It was the first time in human history that we had observed the same cosmic event, both with light and with gravitational waves. We didn't just see it, we heard it. We felt it ripple through space-time. We caught it in every possible way: gravitational waves, gamma rays, visible, light X-rays, radio waves, like hearing and seeing something at the same time, like witnessing a symphony, not just with your ears, but with your entire body, feeling the vibrations in your chest, seeing the conductor's hands, watching the musicians move in perfect synchrony. This was the dawn of multi-messenger astronomy, a new era where we don't rely on just one kind of signal, but combine them all to build a richer, fuller understanding of what's happening in the universe. And what we learned from GW17807 was extraordinary. First, it confirmed what we'd long suspected, that neutron star collisions create kilonovae, bright explosions that forge heavy elements like gold and platinum. The spectral signatures were unmistakable. As the light from the kilonova faded, the fingerprints of these elements appeared exactly as predicted. This was proof, direct, undeniable proof. The gold in your ring, the platinum in your catalytic converter, the iodine in your thyroid. It all came from events like this: violent collisions between the densest objects in the universe, billions of years ago, scattering their atomic treasure across the cosmos. Second, we learned that these mergers can create black holes. As the two neutron stars collided, they briefly formed a hypermassive object too heavy to remain a neutron star, but not quite collapsed yet. And then, in a fraction of a second, it tipped over the edge and became a black hole, swallowing the remnants of both stars. Third, we confirmed that neutron star mergers produce gamma ray bursts, those mysterious, incredibly powerful flashes of gamma rays that we'd been detecting for decades without fully understanding their origin. Now we know at least some of them come from colliding neutron stars. And fourth, we watched as the merger stirred up space-time like a spoon in a galactic teacup. The gravitational waves encoded information about the stars themselves, their masses, their sizes, their internal structure. By analyzing those waves, scientists could infer the equation of state of neutron star matter, narrowing down what might exist inside these extreme objects. All of this from a single event, one collision observed in multiple ways, answering questions that had lingered for decades. It was a triumph of human ingenuity, a validation of theories that had been built on math and speculation, and a reminder that the universe, for all its complexity, is knowable if we ask the right questions, if we build the right instruments, if we look and listen carefully enough. But GW 170817 was just the beginning. Since then, we've detected more neutron star mergers, more kilonovae, each one teaching us something new, each one refining our understanding of how the universe works at its extremes. Neutron stars, it turns out, are natural laboratories. We can't recreate these conditions on Earth. We can't compress matter to these densities in any particle accelerator. We can't generate magnetic fields this strong in any lab. But neutron stars do it effortlessly, simply by existing. And by studying them, we can test the laws of physics in the strongest gravitational fields we can observe. We can probe the behavior of matter under conditions that push the boundaries of our theories. We can explore the frontiers of astrophysics, quantum mechanics, and general relativity, all from a safe, respectful distance. They are testing grounds, cosmic experiments, running continuously, waiting for us to notice, to measure, to learn. And there are practical uses too. Despite being some of the strangest objects in the universe, neutron stars have found their way into some surprisingly down-to-earth applications. Take pulsar timing, for example. By measuring the arrival times of pulses from distant pulsars, astronomers can detect incredibly subtle phenomena. The Halsey-Taylor binary pulsar, discovered in the 1970s, provided the first indirect evidence of gravitational waves. By watching how the two neutron stars orbited each other, scientists could see them slowly spiraling inward, exactly as general relativity predicted. Energy was being lost, not through light, but through gravitational waves. It was a monumental discovery, and it paved the way for the gravitational wave detectors we use today. Pulsar timing has also been used to detect wobbles caused by planets orbiting neutron stars. Yes, neutron stars can have planets. Not many, and not the kind you'd want to visit, but they exist. And by watching the tiny shifts in a pulsar's timing, we can infer the presence of these worlds. Looking ahead, there's even talk of using pulsars for spacecraft navigation. Imagine a future where explorers travel through deep space, far beyond the reach of GPS satellites or ground-based tracking. How would they know where they are? Pulsars, the universe's natural beacons, spinning with perfect regularity, visible across vast distances, each with its own unique timing signature. A spacecraft could use a network of pulsars to triangulate its position like a cosmic GPS system, built not by humans, but by the universe itself. In fact, we've already started. The Voyager spacecraft launched in 1977 carry golden records, time capsules of human culture designed to be discovered by any intelligent life that might one day stumble across them. On those records is a diagram showing the location of Earth, using pulsars as reference points. Each pulsar is marked by its unique timing signal, like a fingerprint. The idea is that any civilization advanced enough to find and decode the record could use the pulsars to triangulate the origin Earth and the time of launch. We use neutron stars to write our return address on a message in a bottle tossed into the cosmic sea. It's poetic, really. These dead stars' remnants of ancient explosions have become our guideposts, our timekeepers, our messengers to the future. But perhaps the most astonishing thing about pulsars is just how calm they are. On paper, they are absurd, city-sized spheres of degenerate matter spinning at hundreds of revolutions per second, radiating energy through immense magnetic fields and pulsing across the galaxy. And yet from Earth, they arrive as steady, soothing beacons, like metronomes, keeping time in the vast silence of space. They remind us that even in the chaotic dance of galaxies and dark matter, there are rhythms, reliable patterns, quiet pulses in the dark. In a way, they're the perfect bedtime companions, not noisy or explosive, just gently persistent. A tap, a beat, a flicker in the night sky. So now we return to the question we began with: what happens after a star explodes? We've traveled a long way since then. We've watched a massive star burn through its fuel, racing through millions of years. In the span of a few pages, we've seen it hit the iron wall and collapse its core, imploding in less than a second. We've witnessed the supernova, the brilliant violent explosion that scattered its atoms across light years. And we've followed what remains, that small dense remnant, 20 kilometers wide, more massive than the sun, a neutron star. We've peeled back its layers from the thin plasma atmosphere to the solid crust through the nuclear pasta layer and into the superfluid core. We've stood, at least in our imagination, on its surface where gravity is so strong that time slows and space bends. We've watched it spin faster than anything that size should be able to spin, sending out beams of radiation like a cosmic lighthouse. We've seen it hiccup and glitch its crust, cracking its superfluid interior, releasing stored energy in sudden bursts. We've met the magnetars, the angry ones with magnetic fields so strong they distort the vacuum itself. And we've watched two neutron stars spiral together and collide, creating a kilonova that forged gold and platinum and scattered them into space. We've listened to gravitational waves. We've decoded pulsar signals. We've traced the path from a simple cloud of gas to a living star, to a violent death, to something new, something strange, something that defies our intuition and challenges our understanding of what matter can be. And what remains is not an ending, not really. A neutron star is not just what's left after destruction, it's what emerges from it. A transformation, not a disappearance. A rhythm, not silence. A question, not a conclusion. Because even after all the science, all the theories, and all the observations, these little stars still ask big questions. What is matter when it's crushed beyond recognition? What does gravity do at its absolute limit? What strange forms of physics are hiding just beneath that crust? Are we seeing the final state of matter, or just the beginning of something stranger? And now, at the end of this journey, maybe the answer is both. Neutron stars show us that even when something ends, something else begins. That there can be elegance in collapse, beauty in extremity, and even a kind of peace in the spinning heartbeat of a dead star. Think about it. A star spends millions of years burning, steadily resisting gravity, glowing softly in the dark. And then, in a moment of violence, it collapses and explodes. But it doesn't vanish. It transforms. It becomes something smaller, denser, stranger, something that will endure for billions of years, long after the flash of the supernova has faded. It's a reminder that the universe doesn't follow our neat categories of life and death, that endings are always beginnings in disguise, that nothing is ever truly lost, only changed. And in that transformation, there's a connection, a deep personal connection that we often overlook, because the iron in your blood, the calcium in your bones, the oxygen you're breathing right now, it was all forged in the fiery deaths that give birth to neutron stars. We are in a very real way made from the same stardust. The atoms in your body were once inside a star. They were created in fusion reactions deep within a stellar core. And when that star died, when it exploded in a supernova, those atoms were scattered into space. They drifted through the galaxy for millions of years, eventually finding their way into a new cloud of gas and dust. That cloud collapsed, forming a new star. That star had planets. One of those planets was Earth. And billions of years later, here you are, made of stardust, made of supernova remnants, made of the same material that forms neutron stars. So, when you look up at the night sky, some of those twinkling points might be neutron stars. You can't see them with the naked eye. They're too small, too dim, too far away. But they're there, spinning silently in the dark, holding secrets heavier than anything on Earth. And every time you take a breath, every time your heart beats, you're carrying a piece of them with you. That's the lesson of the neutron star. That's the message written in its incredible density, its impossible spin, its quiet endurance. Nothing ends. Everything transforms. We are not separate from the universe. We are part of it. We are it. As you drift off tonight, whether you're listening on your couch, curled up in bed, or looking up at the night sky, I hope you carry with you the quiet reminder that the universe is vast, full of endings, full of beginnings, and always, always asking the next question. Neutron stars are strange, yes, but they're also a reminder that even in collapse, even in death, the universe creates something remarkable, something small, something dense, something that spins quietly in the dark, asking questions through its very existence. They challenge us. They remind us that the universe is still full of mysteries, that there are places where our understanding breaks down, where the rules we thought we knew no longer apply, where matter behaves in ways we can barely imagine, and where the fabric of space-time itself is stretched to its limits. And maybe that's what makes them so compelling. Not just because they're extreme or strange or powerful, but because they're part of our story. They are distant, yes. They are alien, yes. But they are also family, cosmic cousins forged in the same fires, shaped by the same forces. From the calm to the catastrophic, from light to darkness, from fusion to compression, from life to death, to life again. That's the cycle. That's the dance. Neutron stars spin in silence, carrying the memory of their collapse and the weight of forces we're only beginning to understand. All of that from a simple cloud of dust. And as you drift into sleep, remember, even in collapse, even in darkness, even in death, the universe creates something remarkable, something small, something dense, something that spins quietly in the dark, asking questions through its very existence. Sleep well, stardust. The neutron stars are still out there spinning in the darkness, pulsing, waiting, holding on to their secrets, and maybe one day we'll understand them fully. But for now, it's enough to know they exist, to marvel at them, to feel connected to them. Because in the end, we are all made of stars. And the stars, even the dead ones, even the collapsed ones, even the strange, dense, impossible ones, are made of us. Good night.